So this is our second lecture on atoms and elements, and this is on periodic table and electronic configurations. And the first thing that we want to do as we're looking at this is to try to understand why the periodic table looks like this. It's kind of a funny shape. It's iconic, right? But even if you blacked out everything in the middle, you would know what you were looking at because it's got that shape. And it's weird, right? If you had 100 elements and you were asked to put them, in a box or a graph or a shape or something, you would not come up with this funny shape, right? You would not just automatically be like, oh yeah, I'm gonna make it look like this. Why not? Right? So this is kind of this is the first question we're answering today. Why are the elements arranged in this funny shape on this periodic table? And the answer actually is that they weren't initially, except that as researchers, as elements were being discovered and researchers were trying to identify connections between the elements and like what made one element different from another element, this is what came out. So it was actually Dmitry Mendeleev who gets credit for this. Lots of people were looking for patterns, but Mendeleev is the one who found the pattern. And here's what he found, and I'm gonna copy this from my lecture notes over here. So he was listing the elements and he was looking at them according to their properties, physical properties, and their mass, right? So he lists them in order of increasing mass, so starting from hydrogen, going up through oxygen. And then he noticed that as you increase the mass there, it actually starts over in terms of physical and chemical properties. So these are the first things we talked about on the first day of class, physical and chemical properties. Things like what kind of reactions do you have? Are you a gas at room temperature? That kind of a thing. So fluorine is heavier than oxygen, but it has properties more similar to hydrogen. And then sodium actually has properties similar to lithium, and so on and so forth until you get to sulfur, and then it repeats again. So this repeating pattern. So everything in this column, all of these are naturally gases at room temperature. So that's a common physical property they share. All of these are soft reactive metals at room temperature. That's a physical property they share. In fact, they are so reactive, they react violently with water and might even light on fire if you stick them in water. These are a little less reactive, but still pretty reactive metals. And then we start moving towards nonmetals. And then everything in this column, if you react it with hydrogen, it has a chemical property of it forms a new compound with the formula of XH3. So NH3PH3ASH3. And everything in this column, if you give it a formula with hydrogen, it makes a formula with two hydrogens. So H2O, H2S, H2SE. So physical properties, chemical properties, they repeat. And so based on this, actually it wasn't based on this. This is the trick. Those ones weren't known yet. And Mendeleev, when he was trying to fit everything to a pattern, everybody was trying to fit everything to a pattern, it wasn't quite fitting. And he was the one, he gets credit because he was the one that looked at this and said, wait a minute, guys. I know why it doesn't fit. It's because you're missing elements. And then he sits down and he says, well, because it's a repeating pattern, clearly. He says, you're missing elements, guys. You're missing this one and you're missing that one. And I can tell you how much they're going to weigh, because they're going to be a little heavier than calcium, right? And a little lighter than arsenic. And I can tell you what their physical and chemical properties are, because they're going to match what's in these columns. And go out and find them, right? That's crazy gutsy. Like, it's one thing to say, here's the data, let's see how it fits. And it's another one to say, oh, there's a hole in your data. There's something you haven't discovered yet. Go find it. Except when they discover it, he says, hey, I should get credit for discovering it because I discovered it in my mind first. Isn't that crazy? So here we go. That's why he gets credit for it. So there are some other pieces missing here, as you might know. This is kind of a rough description of what happened there. But for instance, the noble gases, this column here, hadn't been discovered yet. So that's why they're not included in that particular list. And that's why it's called the periodic table. Periodic means repeating, like a periodical, like a magazine, right, that comes back. something happens periodically, then it repeats. And so that's what this is. This is a repeating table of physical and chemical properties. That's exactly what it is. And so we've grouped these according to their repeating physical and chemical properties. All right, so let's talk about this. Some of these get special names, and you need to know these special names. So for instance, I did mention this last column here. They are called the noble gases. Okay. You need to know that. This second to last column right here, the fluorine, chlorine, bromine, all of those going down. You need to know that these are called the halogens. All right. Some of these other columns have special names that you don't need to know. Like these are called the chalcogens with oxygen, sulfur, selenium. I'm not going to test you on that. We don't have names for these that you guys need to know, but on this other side, we have this first column, which consists of the alkali metals. And if you put those metals into water, we mentioned they react very violently. And after they're done reacting, you're left with a basic solution. Alkali is another word for basic. So that's why they're called the alkali metals. And these are alkaline earth metals. I should say metals. Get rid of this little guy here, don't need him. All right, and then we've got a few just segments here. The segment in the middle, these are known as the transition metals, transitional metals. They're like going to transition us from this second column to that. Sometimes we call it this the third, fourth, fifth, sixth, seventh column, and so on and so forth. And then this section down here, these are known as the, I don't have a lot of space down here, inner transition metals. And they're actually, I'm not sure if you can tell, or if you noticed here, there's a little line right here. And that tells you, oh, by the way, that's where this gets inserted. It goes right here. So you have element 57 in lanthanum, and then you have element 58 in cerium. And so on and so forth till you get to 71, and then it's 72. So technically, this periodic table, if you inserted the inner transition metals where they go, then the whole periodic table would look something like this. Here's your inner transition metals. Here's the rest of your transition metals. There's the rest of your, we call those the main group, and finally the noble gases. That's what the periodic table would look like if we stuck those inner transition metals where they go. Those are the inner transition metals right there. So typically the reason that we put these inner transition metals down at the bottom is so that this whole thing fits really well on an 8.5 by 11 sheet of paper. That's primarily the reason. The secondary reason is that we don't use those a lot, so it's, we just put them down on the bottom. Nobody has to look at them. Most of them are synthetic, and they're kind of hard to find, so we don't use them a ton. So those are the group names you need to know. As columns are groups. The rows are known as families. The columns are groups. The group name of noble gases, halogens, alkaline earth, alkali metals, and then this whole group of transition metals and this whole group of inner transition metals. One little last piece. There's an invisible line that goes right here. And again, this periodic table, I got this from the front page of your course website. This is the one that you use on your exams, right? And that none of this is written in, so you might do that when you first sit down to take your exam, when you do like a brain dump, right? And write down everything that you wanted to remember for the exam before you start. You could do this. So there's this invisible line here that separates all of the metals on the left-hand side from all of the non-metals on the right-hand side. So these are given by physical properties, right? What are the physical properties of metals? How are they different from nonmetals? Anybody know? Like when you think of a metal pan, for instance, right? A metal pot. Oh, Erica's reminding me that we have another category here. If you're on the line, if you're close, if you're like touching this line, then you might kind of have properties of both. In which case we're going to call you metalloids. You have properties of both metals and nonmetals, but we want to figure out what are those properties first. So generally speaking, like think a pot or a pan or something. You're good at haircuts, okay? It's fine. That's going to be made out of metal. And it is probably shiny, right? They have luster. And yeah, they can withstand high heat. And in fact, they'll usually conduct heat. And they'll also conduct electricity. So this is why we use, for instance, copper wire to run our electricity, because it conducts the electricity really well, copper being a metal, right? And we usually use metal pots because they conduct the heat from the heat source to your food very easily. Good. Malleable, which means that you can hammer them into a thin sheet, right? So that's how you get something like a aluminum foil or maybe like a breastplate, right? You can hammer it down and it just takes that new shape. Additionally, along with being malleable, they're ductile, which means you can draw them into a thin wire, just like you can for your copper that runs around your house, right? So to contrast that with nonmetals, right? If you think of nonmetals, something like a good example here, carbon, coal, right? A lump of coal. It is not shiny. There's no luster to it, right? It doesn't conduct heat or electricity. In fact, it'll just try to light on fire if you tried to do that. And if you tried to hammer it into a thin sheet, it would just crumble, right? And if you tried to form it into a wire, it would also just crumble. So it's kind of exactly the opposite. Oh, brittle, yeah. Brittle instead of being malleable and ductile, right? Do not conduct heat or electricity, not shiny, kind of a thing. So the metalloids are in the middle, and each of those kind of is a little bit unique. And I don't want to spend too much time talking about metalloids because, as a matter of fact, there's not wide consensus in the chemistry community whether it's kind of important to distinguish these or even which ones they are. For instance, nobody calls aluminum a metalloid. It's definitely just a metal, right? But silicon is definitely a metalloid. This is kind of our poster child for the metalloids because silicon is not silicone, but silicon is really shiny, like it was a metal, but it's brittle and doesn't conduct heat or electricity. So it's like kind of does a little bit of both. So some can have some properties of both. All right, so metalloids along that line, nonmetals on the right-hand side, metals on the left-hand side. Okay, so that is just kind of an interesting introduction as to what the periodic table is and why it's organized the way that it is. And before we continue, I just want to look over our worksheet just a little bit, and you guys can help me fill this in so that we're just kind of on the same page here. Okay, so I'm going to scroll down. Oops. Oh, one other thing to note, I think I put this on the discussion forums. I got this, I like this periodic table, but I got it from like a British English website. So these are spelled a little bit differently than they are in American English. So if you put these spellings in Mastering Chemistry, it'll mark you wrong. So in Britain, they call it aluminium, but for us, it's just aluminum. So there's this extra I that can go away. And it's the same thing. British English, cesium, but in American English, we just drop that extra A and just call it cesium. All right, so hope you have your periodic tables handy. And you guys can help me. Tell me whether silver, for instance, is a metal, a nonmetal, or a metalloid. Metal. Perfect. What about chlorine? Non-metal. Perfect. It's also, it says additionally give the group or family name. What's the family name for that guy? Halogen. Perfect. Right, so if we scroll up here, we can see, sure enough, there's silver. It's a metal. Specifically, it's a transition metal. I should probably note that. And here's chlorine. It's in this column. It's a halogen. Now, again, you do get this periodic table on the exam, so you never have to memorize the element names or the periodic table at any time. Okay, what about calcium, Ca? Perfect, alkaline, earth, metal. Perfect, it's right here. There's calcium in the alkaline earth. And note there, I mean, there's a lot that are really similar. So don't confuse C and Ca and Cr and Co and Cu and Cd, right? There's a whole bunch. Start with C here. Okay, what about, oh, Cs. Oh, look, I gave you all of the Cs. Cs, which one is that? Alkali metal. Perfect, Danielle. Yeah, that's cesium. Wait, alkali. Yeah. Perfect. And carbon, C. Metal. Excellent. And copper, Cu. Metal, specifically a transition metal. Perfect. What about Cm? Perfect. Yeah, that's an inner transition metal. Cm is curium, right? Here, named after Madame Curie, who is actually the first and only person in the world to ever have 2 Nobel Prizes in 2 different disciplines. She got a Nobel Prize in physics and the Nobel Prize in chemistry, which is pretty awesome. All right, what about Sr? Alkaline earth, perfect. Good. Sb. This is a metal. So Sb is kind of, let's see, Sr is right here. So there's your alkaline earth. Sb is over here. So it's on the metalloid line. You could call it a metalloid if you wanted to, or you could call it just a metal. Additionally, this group right here, and I'm not going to test you on that, but this group of metals, because they come after the transition metals, sometimes we call these the post-transitional metals or the post-transition metals. But that's antimony's right there, Sb. All right. Metal, maybe a metalloid. It's a metalloid on the metal side of the line. Okay, what about N? Non-metal, good. Fi. Good. Non-metal, and it's also a halogen. Sorry, Daniel. Post-transitional or post-transition? Yeah. Either one of those is okay to describe it. All right, GD, what is that? Good. Inner transition. Good. GE. Metalloid. Okay. And FR. Alkali metal. Perfect. Excellent. Okay, so then for B, for the above list of elements, group together those which would behave in a similar fashion. That is, have a similar reactivity. So what are you looking for to determine if something has similar reactivity? What are you looking for there? Same group. Perfect. So if they're in the same column, that's the group, then they're going to have similar reactivity. So Erica says CS and FR, because both of these are in group 1. So they would have similar reactivities. And each of these has a pair. So you guys got CS and FR, and Erica's got also calcium and strontium, because those are both alkaline earth. So they're in that column. What else do you see? All right, we've got AG and CU. Let's have a look. All right, yep, AG and CU are in this same column. So that works there. David mentions Cl and C, but just because they are both nonmetals doesn't mean that they're going to have similar activity, because they're not in the same column. That's what we're looking for, is the right column, right? SB and GE. Let's see. Same story, right? Just because they're both metalloids, so they have some of the same physical and chemical properties as metalloids, doesn't put them in exactly the same group. So we're looking just at the column here. So instead, you've got carbon is in the same column as germanium. So even though carbon is technically a nonmetal and germanium is a metalloid, they're going to share some similar properties, right? All right, and Nicole says we've got GD and CM. That's right, gadolinium and curium, both inner transition metals, picked from the same column. So we can put those together. Does this make sense? nitrogen and germanium. Kind of fun to look at the periodic table and see how many of these are named after places or people you know, right? So germanium is actually named after Germany. Wait, not nitrogen and germanium. They're not in the same column. Nitrogen and Sb, right? Sorry. Carbon and germanium. I did that there. Oh yeah. Nitrogen, Sb. Yeah, you're good. So Germany gets germanium, France gets francium, America, in fact, gets americium, and berkelium and californium. You can tell we had a pretty good atom discovery program going on the West Coast at some point. Many named after people like curium and mendelevium and nobelium. It's kind of fun. Okay, let's see. Which ones are we missing? Whoops. I wrote N and GE right there, and I did not mean to. What would we group with chlorine? Cl. I, that's right. Chlorine and iodine, both halogen nonmetals. Let's see, we got calcium and cesium, carbon, copper. Did we get them all? Looks like, I think so. All right. So that is our explanation as to why the periodic table is set up this way. It has to do with physical and chemical properties and reactivity. But of course, because we're scientists, that's never the end of the story, right? Because then we just have to ask ourselves, yeah, but why? Why is it that there's this funky, like, repeating pattern, and it's sometimes repeats 2 and sometimes repeats a couple more? And what is going on that makes, for instance, the helium atom different from the fluorine atom such that they have these different properties, even though they're both atoms? And so to answer that question, we have to talk about something called electronic configurations. All right, so I'm going to scroll down here, start a new section. So as it turns out, as we discovered previously, your atom has a dense nucleus that consists of all your protons and neutrons and is surrounded by a large squishy cloud, you might call it, a region of electron density. This is where your electrons live. And it's not just a big cloud, actually. It is organized in a very discrete pattern based on the amount of energy available and the size of the atom and a number of factors. But it's organized in a very discrete pattern, and we call this pattern the configuration in which the electrons are distributed. And so here's how we're going to break it down here. So electrons are allowed in discrete energy levels called shells. So there's energy level 1, energy level 2, energy level 3, 4, etc. Those are the shells that they can be in. Within the shells, we have additional subshells. So each shell contains a number of subshells. And more subshells are available with each increasing energy level. Okay. So subshells are categorized as S, P, D, or F type. contained in the shells. S-type subshell, oops, P, D, and F-type subshells. And then within the subshells, we've got, whoops, oh, that's not what I meant to do. Within the subshells, we have, not gonna let me do that. We have orbitals. And orbitals, so each subshell contains orbitals and that contain the electrons, and each additional subshell contains more orbitals. So the S contains 1 orbital, the P contains 3 orbitals, the D contains 5 orbitals, the F contains 7 orbitals. And then from there, each orbital can contain 2 electrons. All right, so with that introduction, here's what this looks like if we drew a little chart here of increasing energy levels. So this would be the lowest energy level. Let's say, oops. Here we go. Energy level 1, energy level 2, energy level 3, 4, and so on and so forth. In energy level 1, we have only available the S-type subshell. It contains 1 S-type orbital, which holds 2 electrons. Whereas in level 2, we have an S-type subshell, again, a new one, a level 2S type subshell, containing a single S-type orbital, which holds 2 electrons. And we also now have a P-type subshell, which contains 3 P-type orbitals, which hold a total of 6 electrons because there's 2 electrons each. In level 3 shell, we have a new S-type orbital, another S-type orbital. It's just a level 3 S-type orbital, subshell, containing 1 S-type orbital, again, which holds 2 electrons, and again, a P-type subshell containing 3 P-type orbitals, which hold 2 electrons each, so it's a total of 6 electrons. But now we have increased our energy levels, so now we also have available an D-type orbital, D-type subshell, I should say, containing how many D-type orbitals? Right here. Each D subshell can contain 5. There we go, 5 D-type orbitals, and hold, on balance, since each orbital holds 2 electrons, how many electrons can the D-type subshell contain? 10 electrons. Hang on a second. I'm gonna have to make this a little smaller so it will fit. Whoops, I said 1 instead of 10. I'm just gonna insert a little 0 there. 10, well, that's not gonna work. All right. Okay, right now this doesn't make any sense to you guys. At least I'm not planning on it. So if it does make sense, then great, but we're still talking about it, okay? So just to show you, the S-type subshell is spherical, okay? It looks like a circle. So here's your 1s, and then your 2s is going to be spherical again because it's an S-type, but it's going to be bigger because it's a level 2 instead of a level 1. All right, so here's your 2S-type subshell. The P's, they look like these little figure 8s almost, and there's 3 of them. So we look at this like there's one on the y-axis, there's one on the x-axis, these are 2 distinct ones, and there's one on the z-axis. So there's 3 distinct p-type orbitals there. And then of course the 3s is the same, it's just bigger, right? Just a bigger sphere. And the 3p is the same, it's just, again, it's just bigger. And then the 3d, these orbitals look really funny. I'm going to draw these individually, but they kind of look like four-leaf clovers, okay? And you can have one that's between the x and the y-axes, and there's one that's between the y and the z-axes, for instance, and one that's between the x and the z-axes, and then there's one that's directly on the x and the y-axes. And then they'll show that there's one that actually is totally different. It looks like a p orbital with a donut running around it. I'm not making this up, I promise. Now, orbitals are kind of funny things. They are not discrete objects, right? It's not like this is a boundary that's holding the electron in, because the electron, I mean, your matter is already at the smallest that it can go. And so orbitals are not objects, but instead these are mathematically defined areas of electron density, is essentially what these are. You don't have to know what these look like, but just to kind of show you these shapes that are in here, and it's some pretty complicated math to show what these shapes are and why they are there. But essentially, what happens when an electron comes and lands on this atom or in this atom, it's going to go to the lowest level available, okay? So the first electron that enters an atom lands in this 1s type subshell. 1s right here, right? And the second one that comes along is going to land in the 2s subshell. So this level 2 is split between the 2s, which is lower level than the 2p's. Well, I drew this as 3 lines because remember there's 3 orbitals in the p subshell. And then the next electrons that come, they have to, if these spots are filled, the next electrons that come, they're going to fill in the level 3s. So here's level 3 is split between the 3s and the 3p and the 3d, which now has 5, 3, 4, 5. 3D, I'm running out of space. And then there's a weird overlap here, the level 4s, because it's the lower part of the 4 ends up being lower than the 3D. And then you have 4p and so on and so forth. Okay, so, whoops, that's too many. Here's your 4p and 4d. Okay, if you're not following along perfectly, it's okay. We're good. But this is just to kind of show the first electron that comes along is going to land in the 1s orbital. And then the second one is also going to land in the 1s orbital. And then once it's full, nothing else can fit. So the next one has to go in the 2s and then the 2s. And once that's full, nothing else can fit. We're going to get 1, 2, 3, and then 4, 5, 6 in the 2p. And once that's full, nothing else can fit. And the next electron has to get dumped into the 3s orbital. And they always go in this order. except as we noted, there's some weird overlap going here between the 3D and the 4S. Happens again with the 4D and the 5S. And there's a little, like a mnemonic device. I can show you how it, you fill the 1S, and the 2S, and then the 2P, and then the 3S, and then the 3P, and then the 3D, 4S, 4P. And at the level 4, you also have access to the F, right? And then 5S, and 5P. At level 5, you should technically have access to a G orbital. Sorry. Although we haven't, the periodic table hasn't been created that far out. After F, they said, let's just call them by alphabetical order. 6H, hypothetically. 7S, 7P, 7D, 7F, and so on and so forth. Okay. So if you just kind of outline these, then you can predict the order they're going to fall by doing this this diagonal thing. So the 1S fills, then the 2S, then the 2P, then the 3S, and this takes care of your overlap. The 3P fills before the 4S, and then it goes back and fills the 3D, and then the 4P, and then the 5S before the 4D, and it just goes in this order, and so on, and so forth. Okay. All right. That is how that goes. So let's do this together just to show how this might look. And the point of this, the promise of this discussion was to explain to us why this funny shape. So let's pick 3 elements that are in the same column, and we can do the electronic configurations for them and figure out, okay, why would they be in the same column? Let's do, what do you think? Let's do fluorine, chlorine, and bromine. Does that sound fair? Fluorine, chlorine, bromine. They've got 9, 17, and 35 electrons. Okay. I'm going to use this as my little cheat sheet here. Except I'm going to take away these arrows because I can't see what's going on. Okay. So here we go. We've got fluorine, chlorine, and bromine. And fluorine's got 9. And chlorine's got 17. And bromine's got 35. Okay. All right. So if we're going to fill an atom with 9 electrons, and they have to fill in the same order, then first, the level 1 shell, the S-type subshell, the orbital there can hold 2 electrons. And so typically we do this 1s with a superscript of 2 to tell us that that 1s orbital contains 2 electrons, okay? And then after that is full, because it only can hold 2, our level 2 S-type orbital will also pick up 2 electrons. And then it's full, right? So we've done the 1s, and then we've done the 2s. And now we can start filling the 2p. And the level 2p orbitals can hold up to 6. But we have already distributed 4 electrons in the 1s and the 2s, right? And fluorine only has 9 total, so we only have 5 left. So I said we've distributed 4, so 9 minus 4 gives me 5. The P can hold up to 6 electrons, but we've only got 5, so we're going to put the 5 in there. It's not quite full. If another one came along, that electron would fall in that spot. but currently this is all we have. So that is how those electrons are distributed in the fluorine atom. Does that make sense? Semi sort of, you following along? Okay, got a couple yeses. All right, let's do it again for chlorine. So chlorine has 17, so it's going to start in exactly the same way because everything fills in exactly the same order here. Do a rough approximation. So we've got 1s, 2, 2s2, 2p. We know it's going to start the same way as fluorine. But now we can fill all 6 of the spots in the 2p orbital. So that's 10 electrons. And now we have 7 more, so we're going to keep going. We're going to fill that 3s spot, okay? So keep going. We've got a 3s, and it can fit up to 2, after the which we're going to start filling our 3p. Okay, so we put in 10 between the levels 1 and 2. And there's 2 more for the 3s spot. And then, so that gives us 5 left, right, to add up to 17. So you're going to get 5 on the P. Is that right, Erica? Is that what you predicted? Yeah, so our 2 plus 2 plus 6 plus 2 plus 5, that gives us 17. So we're going to do it again here with the bromine. And Erica has made a prediction. She says, it looks like our P's end in 5, like fluorine ended in 2p5 and chlorine ended in 3p5. So I think maybe the bromine is going to end in what? What do you think? It'll end with 5 electrons in a p-type orbital. Which level is it going to be in? In level 4. All right, let's try that. Let's try it. Okay, so we've got the 1s is going to have 2 electrons, and the 2s is going to have 2 electrons, and the 2p is going to have 6 electrons. We know that these are going to be filled because the bromine has even more electrons than the chlorine, but they're still start by filling in the same way. So I can't do a superscript, so I've got to do this manually. 1s2, 2s2, 2p6, 3s2, 3p6. And after I fill the 3p's, then I can fill the 4s's. I have to do that before I fill the 3d's. All right, so that gives me 4s. And the 4s level can hold 2 electrons. All right, so just as a double check, we've used 10 electrons there. And that's another 10. So we've used 20 electrons and we still have 15 left. So we're going to keep going. And now it says, oh, hey, you've got to put stuff in the level 3D orbitals. Okay, so 3D, how many electrons can the D-type orbitals hold? They can hold 10, and we've got 15 left, so we'll slap 10 in there. That leaves me with 5, and they're going to land in the 4p, exactly as we predicted. Good job, Erica. 4p5. Okay, so note what we're taking away from this, right? What we wanted to know is why the funny shape? Why is it, what is it about their structure that makes fluorine, chlorine, and bromine behave the same way physically and chemically? And the fact is, it's nothing to do with their protons or neutrons, because those are stuck in the middle. They see nothing. It's everything to do with the electrons, because that's what's on the surface of the atom. And when the atom interacts with another atom or with its environment, it's those electrons doing the interacting. So the electron structure is what dictates these kind of properties. And you see that fluorine, chlorine, and bromine have the same number of electrons on their surface in the same type of orbitals. Each of these has, you might say, 7 electrons in its outer shell, right? The level 2 shell. for fluorine has 7 electrons. The level 3 shell for chlorine has 7 electrons. The level 4 shell for bromine has 7 electrons, right? And the last spot left, if another electron wanted to come in, it would land into this p-type orbital. Does that make sense? Can you guys see that? Okay, excellent. Let's scroll up. We can add just a little bit of information here. You'll notice that we kind of have several distinct segments here. So this first one, these first 2 columns are set apart from this middle brick, which is set apart from this last brick. And then the inner transitions are kind of separated out into their own space. Okay, what's happening here is this first row, this first family here is filling the level, the level 1 shell, S-type subshell. So hydrogen here is 1s with 1 electron. Helium here is 1s with 2 electron, and now the S shell is full. There's only 2 atoms in this row because that's level 1 and it's only got room for 2 electrons. And now we're filling level 2 in the second row. So for lithium, we start filling level 2s orbital with 1 electron, 2s orbital with 2 electrons, and then we skip over to the 2p's and we fill 2p1, 2p2, 2p3, 4, 5, 6. All right. So this first block here with the alkali metals and the alkaline earth metals is also known as the S block because it is filling the s orbitals, right? 1s1 for hydrogen, 2s1 for lithium, 2s2 for beryllium, 3s1 for sodium, 3s2 for magnesium. Jumping over here, the right hand side, of this periodic table, which we continue to call main group. This is the P block because you're filling your p-type orbitals, and there are 6 columns here because you can fit 6 electrons into those p orbitals. Which block are we filling here with the transition metals? That's the D block, right? This is, we saw with bromine, after we filled chlorine with 3p5, argon got 3p6, then we skipped to 4s1 and 2, then we went back to 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, before we could go back to 4p1, 2, 3, 4, 5 for bromine. And yeah, the D block has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns to correspond with the 10 electrons that fill those 5 D-type orbitals. Now, that means the inner transition metals are filling what type of orbitals? Nope, transitions were the D block. So these are the F block. And we didn't talk about it, but the F subshell contains 7 F-type orbitals, which of course each contain 2 electrons. So it contains up to 14 electrons. And you'll notice that this segment is 14 atoms long. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. There is the F block, right? So the rho is the energy level it's filling, or the shell. And then depending on the block, that tells you what subshell is currently being filled there. Now, really good question. We've got something really strange going on with hydrogen and helium, because Helium is not, it doesn't fill a p orbital, so it would be weird to put it there with the p block. So maybe we could put it here. But it doesn't feel like it fits there because it's not really a metal or an alkaline earth metal. It really fits better here because it has the same physical and chemical properties as the neon, argon, krypton, xenon. They're all noble gases. That's why it's put there. So, and then at the same time, you have to ask yourself, okay, what about hydrogen? Hydrogen is not a metal. I know it's here on the left-hand side of the periodic table. It's listed with the alkali metals, but it's not a metal. And a lot of people would rather just put it here. I mean, this is where Mendeleev put it at the top of fluorine, chlorine, bromine, because they're all gases at room temperature. And that actually makes a lot more sense to put it there, right? So there's some funny stuff going on here. The reason that hydrogen usually gets put on top of the alkali metals is because when it makes an ion, it makes a +1 ion, which the rest of the alkali metals do. So when it's reacting chemically, when it has reacted, then it behaves a little bit more like those, even though as an element it doesn't, okay? And then helium is here because it acts a little bit more like these guys. Now you might say, why would helium act like neon and argon and krypton and so forth, even though they don't have a p block? Well, let's look at the electronic configuration of helium and neon and see if we can explain what's going on there. So helium only has 2 electrons, so 1s with 2 electrons and it's full, right? That's helium. Very simple. Helium right here. Neon has 10, so it's going to be 1s is full with 2, and then the 2s is full with another 2, and then the 2p we've got, let's see, if I have 10 electrons total and I've used up 4, I've got 6 left and the p holds 6, so that's it. I can just stick that there and we're done. Okay, what do helium and neon have in common that would make them behave the same way chemically and physically? Erica's got it there. Their outer shells are full. Okay. So we will use the term valence electrons. We'll expand on that in a little bit. That means the number of electrons in your outer shell. Helium only has 2, whereas neon has 8. But that's not as important as the fact that the shell that helium is filling is full now. And the shell that neon is filling is completely full. And it turns out that having a full shell gives you a little bit of stability. So these atoms, all of these with completely full shells, are very stable the way they are. If something comes along to react, they're like, I don't want to react with you. I have the electrons I want. I don't want to share them. I don't need any more. Just leave me alone and I'll be fine. They called them noble gases because the idea was they kept themselves apart from all this common riffraff that's mixing together and making chemical stuff, right? That's as the common people would do, right? Whereas nobles keep apart from all of that, right? So it's the fact that they're full. So helium is full with a full s shell, 1s2. Neon is full with that full level 2 shell that has the s and the p orbitals. But no matter which level you're filling, if it's full, then you're going to be non-reactive, so you're here in the noble gases. Great. Okay, so that is the long story to preface this shorter story. And that is, what you really need to pull away from this is how to look at the periodic table and tell how many valence electrons are around an atom. So the valence electrons are the electrons on the surface, which is to say the outermost shell. Because as you're filling the shells, essentially, you know, your S, your 1s is going to go here, and then your 2s is going to go here. So once you start filling your 2s, you can't see your 1s anymore because the 2s is in the way. and then your 2p is occupying that same kind of shape, and then your 3s is bigger. So every time you advance to a new shell, everything in the shell before it becomes shielded and is inaccessible, and it's just that surface shell that's important, okay? So that's what we call the valence electrons. That's what's on this surface, right? So hydrogen has 1 electron in its 1s shell, and then we fill that 1s shell, and then lithium has 1 electron in its 2s shell. So everything in group 1 has just 1 electron in its valence shell. Okay, so I'm just gonna, this is from your lecture notes, but this is really what you need to be able to do with that. I'm not going to test you on electronic configurations. I want you to have been exposed to them, which I just did. And there's a little bit on your homework because I want you to have a little bit of experience with them. But as a matter of fact, as future potential nurses, 20 years from now, I don't want you to be able to be like, yeah, now I know the electronic configurations and it's been super helpful for my nursing career, because it won't be, okay? But I want you to know why, right? So that's the why behind why everything in this first group has 1 valence electron. Everything in this second group has 2 valence electrons. We are going to totally skip this section of transition metals and intertransition metals and pretend they don't exist for the moment. And then everything in this third column has 3 valence electrons, 4, 5, 6, 7, 8, except of course we know that helium only has 2, right? Okay. Danielle says, don't you just count up from the bottom with all of them? Why are they in different blocks then? I'm not sure what you mean by that question. Can you rephrase that?
Yeah, so I'm just confused. Like, if you get down to potassium, wouldn't you do like 1s, 2s, 2p? I don't know why they're in S blocks if they're potentially going to have P and D and F. Does that make more sense?
Oh yeah. So this is called the S block because that's what's being filled currently, right? So potassium and calcium, let's look at them. Potassium, calcium, 19 and 20 electrons. 19 electrons, 20 electrons, okay. So if I'm filling for potassium, 19 electrons, I start with a level 1 because everything falls in the lowest level. S-type subshell, which has 2 electrons, and then the 2s has another 2 electrons, so we're up to 4. And then I fill the 2p, which can add 6. That gives me up to 10. And then I start filling the 3s. That's going to give me an additional 2, so that's 12. And then the 3p, which gives me an additional 6, that's 19. And then I have to skip to the 4. So 6, that's 18. So then a 4s is going to give me 1 more. So this then, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That's the electronic configuration for potassium. Does that make sense?
Yeah, so in the S block, everything ends in S. P block, everything ends in P, like that.
That is exactly it. That's exactly it. So we call it the S block not because they don't have any p orbitals, but all of these are in the middle, right? These are inner electrons that have nothing to do with how that thing is going to react. And it's these on the surface that are dictating the physical and chemical properties of the element. So S block because I'm currently filling the level S shell. Yes.
Okay, thank you so much. That helps so much.
Yeah, no problem. No problem. So and I'm glad that you asked that question because it gives us an opportunity to look at potassium and calcium and see that, yeah, these really do end in there's only 1 electron here. So everything in that first column ends in 1 electron. So you've got 1 valence electron. You can see how calcium's got 2. If I keep going across, then you start filling the p orbitals, right? So after you fill the 3s1, 3s2, you start filling the 3p1. Now the s and the p together tell you the number of valence electrons because they're still in level 3, right? So for like fluorine, chlorine, as we did here, we said everything together in the level 2 because it's all in level 2, not just because you're looking at the P's, right? And all in this outer level 3, there's 7 electrons. And we're going to skip the D there and say all this outer level 4, there's 7 electrons. So fluorine, chlorine, and bromine each have 7 electrons in their outer shell. You guys see that? That makes sense? Kind of? I'm not saying a yes or a no. Does it make sense that fluorine, chlorine, and bromine each have 7 valence electrons based on the idea that we're not looking just at like the P's from the P block, but everything in that same level. So all of level 2, the outer level, has a total of 7 there. And all of level 3, being the highest level there, has a total of 7. Okay, all right. So let's then look at our worksheet and see what we can see. So the next section on our worksheet says, let's give the element names and the number of valence electrons in these elements. All right, we can do this. Ne, what is that? And how many electrons does it have? That's neon. It's got 8 electrons. Excellent. Na. Sodium. It's got how many valence electrons? 1. Perfect. N. Good. It's got 5. That's nitrogen. Now, something you should know, just for like, it's kind of like being grammatically correct. Element, and this makes me really sad to say this, elements are objects and not proper ones. And so you don't typically capitalize the name of it, even though it's a name, right? You'd say like your name is Mary, so you say capital M for Mary because you're a proper noun. But nitrogen, even though that's like the name of the thing, it's just an object, so you do a lowercase n, which makes me very sad because as a chemist, like working with these all the time, it's like they have personalities, right? And we'll use these like human-based analogies to help us understand the way that they work, and you start to feel like they really are like not real people, but like real objects that should have capital letters just like real people, but they don't, and it makes me sad. All right, what is S? S for sulfur, which has got 6. Perfect. Si, silicon, 4. Good. Se, what's that one? Selenium, which has 6. I don't have to have you guys memorize the periodic table because eventually you'll have most of it. Sr, strontium, which has 2. Excellent. Rn, radon, 8. By the way, did you guys know that we're at risk for radon exposure here in Utah? The granite in the mountains has elevated levels of thorium, which decays radioactively to make radon gas, which escapes, and then radon gas is radioactive and you breathe it, and then you get cancer essentially. So it's of particular interest. You can actually check for it. You can buy like little radon test kits, and you can check to see if in your basement is where the radon would accumulate. You can test your basement and see, and if you've got it, then you just have to like improve your ventilation and help kind of off gas it. But something that everybody should be kind of aware of where we're at. All right, RB, what's that? Rubidium. Good. 1 electron. Br. Bromine. 7. All right. Be. Beryllium. 2. Excellent. Ba. Barium. 2. Those are my favorite jokes. What do you do with the sick chemist? It's a question. The answer is, if you can't curium and you can't helium, you might as well barium. That's really disappointing to not be able to see your faces when I say silly jokes. It's just not the same. All right. Al. Ar. Argon. Perfect. All right. You guys feel like you could do that on an exam? Excellent. Okay, so now here's the next question. From this above list of elements, group together those which would behave in a similar fashion. So this is very much like what we just did here, where you're looking according to column, but now we can be a little more sophisticated and say, well, everything in the same column has the same number of valence electrons. Except the matching groups here are not as clean cut. So what would be grouped together? What do you think? Rubidium and sodium. Yep, those both have 1. Neon and radon. Excellent. There's one more that can fit in that category. Argon. Yeah. What else? Yeah, the strontium, the beryllium, the barium, all having 2 electrons. Good. And sulfur and selenium. And it looks like the silicon, aluminum, nitrogen, and bromine are unpaired, right? We don't have pairs for them. Excellent. Okay, you still with me? All right. We've got just a little bit of time left. So let's talk about electronic configurations for ions. If you will remember from our last lecture that we did online, because there was that windstorm, right? An ion is something that has a charge, right? So when our atom either gains extra electrons or loses extra electrons, it becomes an ion. I'm just going to write that down. Okay, so you did a little bit of this previously when I would give you some atoms or ions and say, how many protons, neutrons, and electrons does this have? I'm gonna copy this over. So this is from earlier on in the same worksheet. And you could say, okay, 77 AS3 minus. I know that AS has 33 protons by definition. So you could say you've got 33 protons. And then because I have a 3 minus charge, that tells me I have 3 extra negative charges, 3 more negative charges than positive charges. So that means I've got 36 electrons, right? And then finally, because the mass shown up here is 77, that means that there's 44 neutrons, because the protons and the neutrons contribute to the mass. Does that sound familiar? Put a little plus there, minus there. Okay. And for 56Mn2+, we can do the same thing. Just as a reminder, we can scroll up and see Mn, manganese, has 25 protons by definition. So I'm going to sneak this in here, 25 protons. And then if I have a 2+ charge, that means I have 2 fewer electrons than protons. So I will have 23 electrons. Note how in these cases, I never change the number of protons because that's what defines the element. If I have a negative charge, I just have to have extra electrons. And if I have a positive charge, I have fewer electrons. And it's because it's the electrons on the surface that are doing that reacting. Okay, and then a mass of 56 means I've got 25 plus 6, that's 31 neutrons. Everybody, did I do that math right? Everybody believe me? Makes sense? Excellent. Okay. So up here, we did electronic configurations for atoms, neutral atoms. But as it turns out, electronic configurations for ions are pretty much the same. Because remember, the electrons are going to fill in the same order, and of course they'll come out in the same order. And so you can just look at that number of electrons and do the electronic configuration based on that. And you can still write electronic configurations for ions. So if we did the electronic configuration for this guy, As3-, we just say, okay, it's got 36 electrons. So that's going to be 1s2, 2s2, that's 4, 2p6, that gives me 10. 3s2, that's 12, 3p6, that's 18, 4s2, that's 20, 3d, 10, that's 30, 4p6, that's going to be 36. Sorry, I'm going to go fill these in. Does that make sense? Everybody with me? So this is the electronic configuration for 77 As3-. So As is normally right here. Why would As make, just hypothetically, why would it make a -3 charged ion? What does it get out of its electronic configuration by picking up 3 electrons? Sarah has got it. She says, and Erica's got it perfect. If you pick up 3 electrons, then you have the same number of electrons as krypton. Ooh. Since they fill in the same order, they have the same stability. Now you have a full shell. And so that's why arsenic naturally makes a -3 charged ion when it makes an ion. Okay, that's a little preview for your next chapter. Don't worry too much more about it because that's after exam 1. But let's practice just a little bit more of this. How many total electrons an ion has, and match them for electronic configurations. This is the last section on your worksheet. So magnesium originally has 12 electrons. So magnesium 2 plus has how many electrons? All right, I've got 2 votes for 14 and 2 votes for 10. Do we have a tiebreaker? One more vote for 14, so it must be 14 electrons. Sarah says no. No, we don't get to decide this by vote. Explain. Nicole says it can't be 14 because 14 is more than 12. Since you started with 12. If you had 14, it would be negatively charged. You have to lose electrons to make a positive. You guys are right. You're right. It's 10 electrons. You got it. Right. You originally had 12. You've lost 2, and that's why you got a positive 2 charge. So now you've got 10. All right. Excellent. You see it. You see it. Okay. Calcium. This does not have a charge, so we can just look it up, right? Calcium is, excellent, you've got it, 20 electrons. All right, potassium with a 1 plus. All right, let's look here. Sorry, I have to scroll up and down. Potassium typically has 19, so with a 1 plus, it's going to be, you all got it, 18. Excellent. And krypton, 36 electrons. Okay. Now on the right hand side, Br minus. Bromine typically has 35 with a negative charge, means it's going to be 36. Okay. Here, David, pay attention on this one, see if this answers your question. So titanium with a 2 plus. Titanium in its neutral state has 22. And so if it has a +2 charge, then it would have to have fewer than 22 electrons. It would have to have 2 fewer, so it would only have 20 electrons. That you're not the first person to make that mistake, so you're totally good. All right, F minus. F naturally has 9. So if it's minus, and it's a little hard to see, it almost looks like it's an extension of that F there, but that's a negative charge. It's got 10 electrons. You're good. And then argon, neutral argon right here has got 18 electrons. Okay, so then, without even writing out our full electronic configurations, we can tell which of these is going to have the same number of electrons, or sorry, the same configuration, because they have the same number, right? So which element, which ion on the right-hand side is going to have the same configuration as magnesium 2 plus? The F minus. They both have 10 electrons, so and they always fill in the same order, so they would have to have the same electronic configuration. Excellent. What about calcium? It's going to have the same electronic configuration as titanium 2 plus. Excellent. What about potassium with a plus charge? Same as argon. Good. And then, of course, that leaves us with krypton having the same number of electrons as the bromine ion. So they would have the same electronic configuration. Does that make sense? I want you to recognize that you don't actually have to write out the configurations to recognize that they'll have the same electronic configuration. That's an important takeaway here, right? That you've been taught about electronic configuration, you could potentially write them out, but you can see that fluorine minus has the same electronic configuration as neon without having to write that out because it has the same number of electrons. Okay, that's the takeaway there. All right. Well,